Okay, thermal stress is besides vibration, thermal stress is another challenge, another headache for stress analysis. Okay, because well, things will expand and contract due to temperature. For example, those are ocean liners, the cruise liner that are running along in the cold oceans. In a hot day or sometime a hot day, the thing might expand, and then in the nighttime when the ocean's so cold, it's gonna shrink, and it may go plus and minus up to 1 meters. Okay, so all all the components has to design based on the thermal growth and how it shrinks in the wintertime. We call that in the industry, we call it steps and gaps. So everything has to be nicely designed to accommodate those movement. Let's say, for example, a bridge. I'm sure any bridge that we build right now, one side is fixed, the other side is a sliding joint. Okay, so in a hot day won't buckle, and in a cold winter day won't shrink, and it fell short. Okay, so in this chapter, we're gonna go through some examples on spring elements only, because the thermal stress, if it goes with some other complicated geometry, it may be very hard to simulate by hand calculations. Okay, so right here, we assume there's an unconstrained member. There's nothing constrained to it. So now, when the uniform member is subject to a uniform increase in its temperature, it's going to increase by little delta. So we have a few new terms to learn. Okay, for an unconstrained member, if there's a uniform change in the temperature, the change of length is given by delta T, which is alpha, T, and L. Okay, what is a delta T? Is a change in length. Okay, T is a uniform change in temperature. In my class, we only assume uniform temperature change. I know it's just quite an assumption that we should consider. And if you have different temperature along the bottom, or it takes too long to calculate, because every temperature change you have to assume is one element. Okay, don't worry. In this class, we only consider uniform change in temperature, and also the coefficient of thermal expansion. Okay, guys, every material have their unique coefficient of thermal expansion. That's why if you put two different materials together, even though they snug fit, they fit so well in a regular temperature, when it heats up, two different materials have two different kind of alpha. Okay, depends on the situation. They might stress itself. Okay, so this is one of the questions in ANSYS lab, I believe, right? So the answer is right here. The coefficient of expansion is different. Like for example, let's say you want to open the lid of a jam jar stuck. Okay, you can't open it. So what? You run that thing over hot tap water. So the metal lid expand faster than the glass jar, so you can easily open it. Wow, that's one of the many practical examples. Okay, let's assume the actual direction. Okay, the string is a delta over original length. Okay, in this case, we just move L over here. So alpha times T is the string over L. Okay, when the structure is free to move. It's not constrained anywhere. The uniform change in temperature will not result in stress because, well, it's free to grow, right? Nothing is going to stop it. But that's not the case most of the time, okay? This is being stopped by something. So we have store stress, store energy within the system. Yeah, that's right. That's the one. That's what I'm just talking about. You know, when it's not free to move, it's resulting in some thermal stress. Again, it's just reword what I said. Same thing. You know, when it's constrained, you have stress in the system. Okay, now again, this term is very similar to you. Okay, very familiar to you. Okay, we learned that long time ago. We have to introduce a new terms right here. And how do we define that? Okay, note, this is the, again, this formula is developed by many scientists, many FEA experts. They spend years study to develop that. Now we are lucky when we just use it. B, remember, is the strain displacement relationship. Again, we have a different symbol here. In my previous lecture, B, okay, I think I used D for that to define that strain displacement matrix. This is the elasticity strain of the system. So we take the integral of this term based on the, we developed this long time ago, okay? And we have constant Young's modulus, okay? We take the integral, we get this, E times alpha TA. Again, you don't have to develop this. This formula is given, but you must know how to use them. Okay, let's see how we use them. We have a system right here. That one-dimensional bar is fixed at both ends and is subject to a uniform increase on temperature with 50 Fahrenheit, as shown on the left. Okay, determine the locations, determine the reaction at each end and the axial stress in the bar. Okay, first step, we define the stiffness matrix. This is AE over L. Okay, area is 4 inches square. Elasticity is the 30 times 10 to the 6. The total length is 1 feet, right? Now one element is 12 inch by half, so it's a 6. So we have the stiffness matrix. Don't worry, the second stiffness matrix will be the same. And for the force, okay, okay, right here. Do we have any external applied force right here? Nothing. The only force we have is the thermal force only. And we use this equation right here. We just use it. Okay. K2 is the same thing. We assemble the K global matrix. And we have the thermal force. See, that's the first term. We put it right here. And also the second term is the same as first term, right? So we put it right here. And the lower term of the first term cancel out with the upper term of the second force, so it becomes 0. And then this is the reaction force acting on the beam. We know U1x and U3x is 0. So we multiply that. We solve for, it's just one term, right? We solve for U2x, and we solve, oh, U2x is 0 as well because due to symmetry. Apply boundary condition. Yeah, oh, basically nothing is left, you know, everything just boom. The whole matrix just vanish. Okay. And then we calculate that based on the formula. We solve for this. Oh yeah, that's right. The reaction force on the end is 42,000 pounds. Right? And then the stress is the force over area. We have a compressive stress of 10,500 psi. This problem is too easy for you. Let's do a more challenging one. Ah, I like that one. Okay. Now we have 3 bar elements. Okay, they all tie together. By the way, am I too fast, guys? Any questions so far?
I have 2 questions.
Yep.
So for the previous question, the last line where it says, yeah, right there, where the negative 42,000, 0, and the 42,000. When you bring that matrix, the 42,000, over to the other side, wouldn't it be the transverse of it if it goes past the equal sign? Or no? And when you're isolating for F, the F matrix.
When I isolate the F matrix, when I put that over the other side,
yes,
then it was negative. After I put it on the other side, F1x becomes 42,000 positive. And then F3x, when I put that over to the other side, F3x becomes negative. Yeah.
Okay.
Right? And then I draw the free body diagram. F1x, okay, positive is to the right, negative to the left. So it's squeezing 42,000 because 42 here, 42,000 here. So it's they cancel each other so that body is a stick in the space. It's not moving anywhere.
Okay.
Yeah. Okay, cool. Let's move on. Now, this is a more complicated problem right here. We have a system. Okay, we have load bearings on both sides. Okay. And then one side, it's all tied together. There's 3 bar elements. The middle is tied together. And then let's check this out. What's going on here? The bar assembly show. Okay, bar 1 is subject to a temperature drop of 10 degrees Celsius. So it's going to shrink. Okay. And the bar is an aluminum. So from here, you know that already. Bar 1 and 2, bar 2, 3, they will have different stiffness matrix. Bar 2 and 3 is a brass with a, you see, different thermal coefficients. So they're gonna fight. Okay. Oh, different area as well. Okay, let's do it one at a time. K1, AE over L. Okay, that's the scale factor. Thank you. The beauty of this is all the stiffness matrix always the spring element matrix 1, 1, negative 1, negative 1, so it makes it so much easier. And for the elements 2, AE over L, well, just same formula, but different values, different AE over L. right here, you don't have to repeat the same thing. You can just say K2 equal to K3, okay? And you can, even though you can add them together, you just say 6, 6, and -6 is good enough because they are sharing the same note, 2, 3, 2, 3. Now, this is the tricky part, okay? F1, we have the different alpha, right? Different alpha. Excuse me, guys. I'm just wondering how come F2 has no force. Let me see. Ah, that's it. Okay. In this case, look at that. Even though elements 2 and 3, it gives you a alpha. Okay, but it doesn't say there's a temperature drop to it. Only bar 1 is subject to a temperature drop. Okay, so that's why there's no thermal force in elements 2 and 3. There's only thermal force on the elements 1. So that's why there's no thermal force here in elements 2 and 3. Okay, we add those together. This is the thermal force for elements 1. This is a thermal force from elements 2 and 3. And this is the reaction force we're looking for. We know that F1 is stopped by a wall, so we have to calculate that. And also same as F3. And somehow F2, the middle portion of it, is not subject to any external force. So we can assume that is 0. Okay, and then we put the stiffness matrix together. Okay, apply the boundary conditions. What happened though? We only down to one term, one equation, one unknown. And U2x is this value. Okay, we sub everything back to equation 1 because we want to know what is F1x, right? We sub that term into equation 1, we got F1x. And we sub that term into equation 3, we get F3x. Remember, that's a total force of F3x. But F3 is shared by 2 members, right? So each bar will give you 5.67 kilonewton. Always remember giving units, okay? Now we have the force acting on the elements, right? And we divide it by the area, we get a stress. And that's the end of the problem. If you get that, you get perfect. Thank you. Any questions?